Today we start chapter 4, and it's all about solving systems of equations, and then eventually another video we'll do the review of polynomials and exponents. But solving systems of linear equations, in other words, these are two lines, and either they're going to intersect, they're not going to intersect, or they're going to lie right on top of each other. So you can have other systems of equations. You can have two parabolas that intersect, you can have sine curves that intersect each other, but let's start with the very basic. Let's start with systems of lines that may or may not intersect. So a system of linear equations can share a common point. Whatever their common point is, that's the solution to the system. When you graph them, that will be the point where they intersect. And there's three basic ways of solving these systems, and we'll go through all three of them in the course of the next few minutes. One of them is by graphing. You just graph the two equations, find their point of intersection. If there is a point of intersection, that's the solution to the system. Another way of doing it is substitution. You, quite literally, substitute one equation for a variable in the other and solve. So the idea is to take something that has two variables, get it down to one variable, solve for the one variable, go back and substitute. All right, then the last one is elimination. You add the two equations together to eliminate one of the variables, and then again, substitute back to find the other. Sometimes that third one is also called a linear combination, and that's how you solve. So one way to do it is graphically. So here's a very basic one. The book starts with some very basic stuff, so I will start with that as well. Suppose you're working 16 bucks an hour, right? P equals 16x. That's how much money you take home before taxes. X hour is $16 an hour. So suppose you were paid $128. How many hours did you work? So you notice over here there's two equations. The red line up at the top is the $128. The blue line is you working your way through. So after 1 hour, you've earned 16 bucks. After 2 hours, you've earned 32 bucks. After 3 hours, 48 bucks, and so forth. When will you have reached $128? That'll happen after you work for 8 hours. So 8 hours, $128. You can see there's two lines in this system, and that's where they intersect. They intersect when I hit 128. That's at 8 hours. So this is what the solutions can look like. The first option is that there's no solution. So we had talked in the last unit about parallel lines. Parallel lines have the same slope. So the red line and the blue line are parallel lines. They have the same slope. They'll never intersect. No solution, right? Two people are running. They start at different places, but they run at the same speed. They're never going to intersect each other. All right, the second option is that there's one solution, so the two lines intersect exactly once. The third one actually has two lines on it. You don't see the red line, it's underneath the blue line, but what happens is you have two different forms of the same line, and so anything that works in one line works in the other. Now you notice that it says infinitely many solutions, it doesn't say all real numbers, and that's simply because there are plenty of numbers that will not work. For example, look at 0, 0, right? 0, 0 is a point over here, is not a point on the line. So whatever this equation is, putting in a 0 for x and y won't make either of those statements true. Okay, so while there are infinitely many solutions because there's an infinite number of points in the line, not every real number will work. So let's solve this one by graphing. You're going to see this one pop up several times as we go through. So solve by graphing. X plus y equals 4, x minus y equals 2. We have a couple of options. We can turn them both into y equals mx plus b form and graph. We could plot a couple of points. For example, on this first line, I know that if x is 4, y must be 0 because 4 plus 0 is 4. And I know if x is 0, y must be 4 because, again, 0 plus 4 is 4. So right away, I've got 2 points. There's 4, 0, and then, actually, that's 0, 4. And this is 4, 0. Okay, and I can plot some points in between if I want. And I've got a line. Again, like I mentioned, I can't see the lines that I'm drawing, so I'm doing my best to make them go through the points. You should grab a ruler and a piece of that graph paper that I posted on Canvas to be able to make nice, accurate lines. All right, let's take a look at the other one. The other one is x minus y equals 4. So I know if I put a 2 in for x, 2 minus 0 is 2, so I know it goes through 2, 0. What happens if I put a 0 in for x? If I put a 0 in for x, 0 minus y equals 2, so y must be negative 2, right? 0 minus a negative 2 is 2. So there's 2, 0. There's 0, negative 2. And I graph my line. Now, you can see where it intersects. The two lines intersect in a point. The downside of doing this by graphing is that your solution is only as accurate as your graph is. So here is my point where they intersect. It's 1, 2, 3 to the right, and 1 up. Now see if that works in both equations. In the top line, if x is 3 and y is 1, 3 plus 1 equals 4. That's good. On the second line, if x is 3 and y is 1, 3 minus 1 is 2. So it works in both of them. Graphing equations and solving by graphing is good if you have nice, tidy solutions like 3, 1, and you've got a nice grid, and you're graphing with a ruler, and everything works out nicely. Okay. Not everyone will work out that nicely. And we'll take a look at a couple of cases. All right, look at this one. The first one is already set up in y equals mx plus b form for us. So the y-intercept is 5. So let's go 1, 2, 3, 4, 5. There's my y-intercept. And my slope says go down 3 and to the right 1. Right? Because again, remember we're talking about change in y over change in x. So go 3 in the negative y direction, 1 in the positive x direction. 3 in the negative y direction, 1 in the positive x direction. And we connect our dots. All right, the second line, we got to solve that thing for y. All right, so if we're going to do this in y equals mx plus b form, we got to solve that thing for y. So maybe let's subtract a 2x from both sides. And I get negative y, don't lose the sign, equals negative 2x plus 5. Divide everything through by negative 1, and you get y equals 2x minus 5. So y-intercept is negative 5. And the slope is 2. So a slope of 2 means up 2 to the right 1. So up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. I'm going to do a few points here so that I get enough to make a somewhat accurate line. There we go. All right, so here's my solution point right in there. 2 to the right, 1 down. All right, try and see if it works in both equations. Does negative 1 equal negative 3 times 2 plus 5? So this will give me negative 6. Yes, negative 6 plus 5 is negative 1. Try it on the second line. 2 times 2 is 4 minus a negative 1. And yes, that equals 5. So my solution is 2, negative 1. Look how nicely they work. All right, look at this one. X plus y equals 3, and 2x plus 2y is 10. So I'm going to just work on intercepts here. If x is 0, y is 3, right? 0 plus 3 is 3. And if y is 0, then x is 3. So this line goes through 0, 3, and it goes through 3, 0. All right, look at the other one. 2x plus 2y is 10. So I'm going to do the same thing. I'm going to plot in a couple of points. If x is 0, then y must be 5. Right? 2 times 5 is 10, plus 0 is 10. And I'll bet you it works the other way too. If x is 5, 2 times 5 is 10, so y is 0. So there's 0, 5. There's 5, 0. Oh, look at that. Those two lines are never going to intersect each other. And if you were to solve them both for y, the bottom one would end up being 2y equals negative 2x plus 10, or y equals negative x plus 5. The line on the top, the one that was graphed in red, ends up being y equals negative x plus 3. So you notice they both have a slope of negative 1, except they got different y-intercepts. So what we say for this is that there's no solution. All right, so that's solving systems by graphing. Let's keep going and try solving systems by substitution. All right, if I'm going to solve by substitution, I'm going to solve for one variable in terms of the other, and then substitute to try to get rid of one of the variables. So here comes that equation that we started with at the beginning of the last section. x plus y equals 4, x minus y equals 2. I can choose to solve either the top one or the bottom one for either x or y. In this case, I think I'm going to take the bottom one and solve it for x in terms of y. So what I'm going to do down here is I'm going to add a y to both sides, and I'm going to get x equals 2 plus y. Then I'm going to come up to the top line, and I'm going to replace that x with a 2 plus y. So look what happens when I do that. I get 2 plus y equals 4. So combine my y's together, subtract a 2 from both sides, and then divide both sides by 2. And I get y equals 1. Right, a little bit of back substituting, and I can figure out what x is. So if y is equal to 1, let's go back to that top line. X plus, instead of y, we'll write 1. X plus 1 equals 4. Subtract a 1 from both sides. I get x equals 3. So I'm going to write my answer in ordered pairs. X equals 3, y equals 1. See if that works for the bottom line. 3 minus 1 is 2. If you go back a couple of slides, you'll realize that that's the same answer we got by graphing. So we're using different methods to find a solution, but the solutions that we find are going to be the same regardless of what method we use, as long as we obviously do them correctly. All right, look at the first one here. The first one is already kind of set up for us. It says y equals x plus 2 on the bottom, so why not take this x plus 2 and put it here in place of y. So x plus, instead of y, I'll write x plus 2 equals 6. Now notice what happens is I got rid of that y. I'm down to just one variable. So 2x plus 2 is equal to 6. If I subtract the 2 from both sides, 2x equals 4, or x equals 2. And now we already know that y is equal to x plus 2. So if x is 2, y is equal to 2 plus 2, which is 4. So it looks like my solution is x equals 2, y equals 4. I can try it up on the top row. 2 plus 4 is 6. On the bottom row, 4 is equal to 2 plus 2. Oh my goodness, look at the next one. We got fractions in this one. So what do we do? Well, we got a couple of options. One is we could multiply that top row by something to get rid of the fractions. If I have to solve for something, I might try to solve that bottom row for x in terms of y. So add a 3y to both sides, and I get x equals 3 plus 3y. Now I can come up here, and I can replace that x with a 3 plus 3y. So my goal is to solve for one of the variables, and then substitute. Now I could have done the other one too. The only thing is I would have gotten a y equals a negative x over, or an x over 3, and now I'd be introducing even more fractions. So doing it this way reduces the number of fractions. Not completely, but a little bit. So the x is replaced by a 3 plus 3y. So let's write a 3 plus 3y. And then minus 1 half y equals 2. All right, let's move the 3 over to the other side. 2 minus 3 is negative 1, so don't lose the negative sign. How do I do 3y minus 1 half y? Well, I'm going to need a common denominator. Looks like 2 is a good common denominator. So that one already has a 2 as a denominator. 3 is the same thing as 6 halves. So I get 6 halves y minus 1 half y. Well, 6 of them minus 1 of them is 5 of them. So I get 5 halves y equals negative 1. How do I get rid of that 5 halves? Multiply both sides by the reciprocal. Or you can think of dividing, but sometimes multiplying by the reciprocal is nicer. So I'm going to multiply this side by 2/5 and this side by 2/5. All right, so I get y is equal to negative 1 times 2/5, or negative 2/5. Now it says up here that x is equal to 3 plus 3y. So x is equal to 3 plus 3 times negative 2/5. 3 times negative 2 is negative 6. Remember, we multiply the top. Bottom stays the same. Look, I need common denominators here again, too. In terms of fifths, 3 is the same thing as 15 fifths, right? 15 over 5 is 3. So 15 fifths minus 6 fifths is 9 fifths. So my claim is that x is equal to 9 fifths and y is equal to negative 2 fifths. Is that correct? Well, let's throw it back in that top line and see if it makes any sense. It says x minus a half of y is 2. So x, which is 9 fifths, minus half of negative 2 fifths is negative 1 fifth. 9 fifths minus a negative 1 fifth. 9 minus a negative 1 is 9 plus 1, which is 10. And sure enough, 10 fifths is 2. So as goofy as this answer looks, that is the correct answer to the problem. And one of the reasons I did this is because I want you to see that, yes, you will end up with fractions sometimes as part of the answer. And that's okay. Leave them as exact values. This one, you can actually turn 9 fifths into a 1.8, and it's exactly 1.8. But if you get things with thirds and sevenths and ninths and stuff like that, leave them as fractions or what we call exact values. Hi, how about these two guys here? The other thing I should point out before I move on to this one is that this would be a hard one to do by graphing, because if you're going to look at those little graph grids, how are you going to tell the difference between 9 fifths and 8 fifths or 9 sixths? They're very hard to tell unless you have a gigantic piece of graph paper that the increments are actually broken down into fifths and you're using really precise instruments and sharp pencils to graph it. Otherwise, there's no way I'd be able to look at a graph and see, oh yeah, it's 9 fifths on the x and negative 2 fifths on the y. I could give you an approximation, right? It's close to 2 and it's close to negative half, but not that precision from graphing. So sometimes graphing is nice and easy and quick, but sometimes it doesn't give us those types of solutions that we want. All right, let's pick one of these to do. I don't know, how about letter D? So we got an x plus 5y is 6. We got negative 2x plus 6y is 2. Which one am I going to choose to solve for? Well, on the top, if I solve for y, I can see that I'm going to end up with 6 fifths and 1 fifths, and I'm going to have to then substitute them into the bottom line. So maybe I'll solve the top line for x in terms of y. So I'll subtract the 5y from both sides and get x equals 6 minus 5y. Right? If you want to write the minus 5y on each one, that's what I get. So I'm going to replace this x over here with a 6 minus 5y. Now don't forget that there's a negative 2 already on the outside. So negative 2 times 6 minus 5y plus 6y is equal to negative 12. Okay, so I get negative 12 plus 10y plus 6y equals negative 12. Right? Don't forget when you distribute that 2, the negative goes with it. So negative 2 times 6 is negative 12. Negative times a negative is a positive. All right, what can I combine? I can combine my y's. I get 16y minus 12 equals negative 12. And a funny thing happens. When I add a 12 to both sides, I get 16y equals 12 minus 12 is 0. So y is 0. Is that possible? Sure. Right? 0 is a real number. 0 can be one of the answers in a problem. So it's not wrong if you get y equals 0. Just check your work at the end. Right? If I come back up to the top, x plus 5y is 6. So x plus 5 times 0 is 6, which means that x is equal to 6. So if I did this right, x is 6, y is 0. Nice thing is I can go check my work. 6 plus 0 is 6, and then on the second row you can see negative 2 times 6 is negative 12. Plus 0 is negative 12. So is it okay to get 0 as one of the values? Yes. All right, the only other thing before we do the applications is, what do I do with letter F? One of the things you might want to do is clear out the fractions first before you go to work with this. So for the first row, I might multiply everything through by a 6, because a 6 will clear out both a 2 and a 3. On the bottom row, multiply everything through by a 4. Just don't forget to multiply both sides. So like 6 over 2 is 3, so I get 3x. 6 over 3 is 2, so 2y. 6 times 1 is 6. And then on the bottom, 4 times a quarter is just 1x. 4 times a half, 2y. 4 times 5 halves is 20 halves, which is 10. Now that looks like a friendlier solution, a system to solve. All right, let's do a couple of application problems, and then we'll do the next section in another video. So I've got 2 students going to a basketball game, 4 tickets and 2 bags of popcorn, $14. 5 tickets and 5 bags of popcorn for $25. Find the price of a ticket, cost of a bag of popcorn. So the first thing is, what is it that I'm trying to solve for? It says find the price of a ticket and the price of a bag of a popcorn. So maybe I'll use a T for ticket and P for popcorn. So these things are not numbers of, it's price. So when you define your variable, we're going to be defining the variable as the price of things. So let's take a look at the first group. First group buys 4 tickets and 2 bags of popcorn, and it costs them $14. So the cost of 4 tickets, the cost of 2 bags of popcorn, $14. Second group buys 5 tickets and 5 bags of popcorn for $25. So now I got myself a system. All right, if we're going to solve this thing by substitution, I don't know, let's take this bottom row maybe and solve it for the popcorn. So if I subtract the 5 ticket from both sides, I get 5p equals 25 minus 5t. Divide everything through by 5, right? Divide everything through by 5. And you get p equals 5 minus t. Now we're going to replace this p up here with a 5 minus t. So let's take a 4t plus 2 times, we said we're going to replace that p with a 5 minus t, and that gives us 14. 2 times 5 is 10. Don't forget that's a minus over here. 2 times negative t is negative 2t. And then combine the t's. 4t minus 2t is 2t. T equals 2. So if t equals 2, then the cost of the popcorn is 5 minus 2, which is 3. So the price of a ticket, this must be a high school basketball game, $2 for a ticket to the game, $3 for a thing of popcorn. All right, let's see if that works. 5 times 2 is 10, 5 times 3 is 15. Yep, that adds up to 25. 4 times 2 is 8, 2 times 3 is 6, 8 plus 6 is 14. So $2 for a ticket to the game, $3 for popcorn. All right, last application problem. I got a wildlife management center, cares for birds and deer. Animals have 25 heads and 74 feet, and I think it's important to mention none are missing either one. How many of each type of animal are at this station? Now, the first question is, how many heads and how many feet do birds have, and how many heads and feet do deer have? Well, each of them has only 1 head. However, they have different number of feet. Birds have 2 feet, deer have 4 feet. So if I've got heads and feet, that's not what I'm solving for. First question is, what am I solving for? How many of each type of animal? So let's have birds and deer. Right, each bird has 1 head. Each deer has 1 head. If I add them together, I get 25. So that's another way of saying that there's 25 animals at the station. Then how about feet? So my first line is about heads. My second line is about feet. All right, the birds each have 2 feet. The deer each have 4 feet. If I add them together, I get 74. That's my system of equations. Now I have to solve it. Well, this one's not bad. All right, look at the first line over here. Subtract the d from both sides. 25 minus d. In other words, if you find out how many deer you have, the birds are 25 minus that number. All right, let's substitute that in here. So I get 2 times 25 minus d plus 4d is 74. So 50 minus 2d plus 4d is 74. I can combine the d's together. 4 minus 2 is 2. All right, subtract a 50 from each side. I'm going to move up to the top of the next column here. D is equal to 12. So if there's 12 deer, then there's got to be 13 birds. And you can go back into that second equation and check it. It turns out it checks out. All right, so this ran a little long. We'll break it apart and we'll do the solving systems by elimination in the next video.